Hello all, my name is Putu Arindra, and now we will discuss about the methods of modern alloy production, and my main reference is the book Metallurgy for the Non-Metallurgists. Chapter 5.1 Effect of Alloying on Solidification. The solidification of alloy is a complex process, and it is most easily understood by examining the solidification characteristic of alloy differ from those of pure metals. Solidification of pure metals. When a pure metals begin to melt, the solid liquid mixture stay at the melting point temperature until all of the solid has completely melted. The amount of thermal energy needed to complete the transformation from solid to liquid is divided by the latent heat of fusion of a material. Conversely, pure metal give up the latent heat of fusion and solidify at a single temperature. If a pure metal is melted and allowed to solidify in the melting crucible, a thermocouple placed in the metal during solidification could trace a cooling curve. During the early stage of solidification, the temperature may fall slightly below the melting point of the metal. This phenomenon is referred to supercooling and undercooling. During supercooling, the freezing process is arrested because not enough heat of fusion is released from the liquid to sustain the transformation from liquid to solid. When solidification does begin, the temperature recovers to the melting point temperature and remains constant until after the metal has completed the transformation to the solid state. A slightly different cooling curve can be observed when the molten metal includes some solid impurities. These impurities promote solidification by serving as nucleation sites, such that removing atom can anchor themselves into these impurities, therefore only some undercooling. Although it is possible under very closely controlled conditions to cool a metal far below its melting point. The extent of undercooling experienced in practice is usually very small. This is because commercial melts always contain some sort of nucleating agent. Most often this agent will be the wall of the mold itself. However, other agents may be deliberate add to the melt to control nucleus event and the degree of undercooling. Such addition of especially important in controlling the solidification characteristic of certain alloy casting, such as cast iron, for example. It is also important to point out that the undercooling of supercooling of liquids is common phenomenon, while the superheating of solids is not. Look at a liquid nucleus from much more readily when a metal melts than do solid nucleus when a solid cools. Look at liquid nuclei from first on the surface of solid to spread out over the metals. Diffusion rates are also much higher in liquid, so melting typically occurs more rapidly than freezing. Solidification of alloy. The solidification of alloy is more complex than of pure metals because the different elements in alloy possess different melting temperature. Pure metal freeze and melt at the specific temperature. The massy zone represents the temperature extreme between which is two phase solid or liquids composition is present. The temperature at which solidification begins is called liquidus temperature, and the equilibrium temperature where solidification is complete is called the solidus temperature. Different alloy composition have different liquidus and solidus temperature. and the lines that appears on a binary phase diagram that different this region from each other are referred to as liquidus lines and solidus lines. Repressively, when some of the liquid's metal begins to solidify, the technical term from this event is freezing. Freezing continues until solidification is complete. For any given alloy composition, the difference between the liquidus and solidus defined by freezing range of the alloy. However, some alloys have a unique alloying composition that eliminates the massy zone completely. These alloys are referred to as authentic alloy. Authentic alloy have a specific melting point that is lower than the individual melting points of either of the constituent elements that comprise the alloy, and this can have important particles consequence during casting. In fact, alloy with near authentic composites are the dominant alloy used by foundries in the shape casting of components. For example, cast iron alloy that use the iron carbon authentic aluminum silicones alloy for another example of major family of the shape casting alloy with authentic point. Alloy that possess relatively wide freezing range can be prone to void formation during casting, while alloy composition near authentic melting points where the freezing range is much narrow can have clear advantage in casting specified shapes or geometrics under certain conditions. This is a particularly important consideration in aluminum silicon alloys, which have been used for decades in the automotive industry for casting engines block. Aluminum silicon alloy are used in this application primarily to reduce overall vehicle weight and to improve fuel economy. The freezing ring is strongly depend on the silicon concentration in this alloy, and pouring of steaming temperatures as always like to be higher than the liquidus temperature of alloy. This occurs because some amount of heat unavoidably lost while the alloy is transferred to the molds during pouring, and the temperatures cannot be allowed to drop below the liquidus temperature of alloy before the pouring process is complete. Otherwise, partially solidified material would be transferred into the molds, and this could have very serious consequences during the pouring of turning operation itself. The number of degrees to which the alloy heat above the liquidus temperature is referred to as a superheat. The amount of superheat is typically in the neighborhood of 25 to 110 degrees Celsius above the liquidus temperatures, depending on the particular alloy composition and this interest method of casting. For the reason, liquidus temperatures may be obtained for the appropriate phase diagram and used to help establish the correct pouring of turning temperatures for the alloy composition that is selected. There are many methods that can be employed for the melting and casting of metal alloy, and the method that is chosen between strongly depends on the type of alloy that is selected and the intent application. Okay, we next to chapter 5.2, solidification structure. The solid-liquid interface during solidification is normally exhibited on one of the three types of crystal grow in the liquid: planar, cellular, and dendritic grow. When the liquid ahead of the solid-liquid interface has a positive temperature gradient, heat is removed from the liquid by conducting through the growing solids. Because the temperature gradient is linear and uniform perpendicular to the interface, a smooth interface is maintained and the growth is planar into the liquid. When there is a temperature inversion and the temperature decrease ahead of the solid-liquid interface, then either circular or dendrite growth will occur. The difference between these two is matter of degree. Small decooling then to produce cellular growth, while large undercooling then to produce dendritic growth. In pure metals, undercooling can result from thermal supercooling, while in alloys it can result from combination of thermal and constitutional supercooling. Thermal supercooling, cellular growth. When the advanced planar solid-liquid interface become unstable and a small spikes appear on the interface that then grow into a circular type structure, the planar surface become unstable because any part of the interface can grow ahead of the remainder enters a region in the liquid that is at a lower temperature. The initial spike that remains insulated at first because as they grow by solidification, they release the latent heat of fusion into the eject liquid, casting a localized increase in the temperature. Consequently, parallel spike of almost equal spacing advance into the liquid. Dendritic growth is a further manifestation of cellular growth in which the spikes develop side protrusion. At still higher undercooling and higher growth velocity, the cells grow into rapidly advancing projection, some stem of complex geometry. Dendrites are small crystalline nut shaped like pinch trees, so names after the Greek word dendros for tree. The termites have a primary arm with secondary and terminal arm that branch from it. The spacing of the secondary arms is proportional to the rate at which heat is removed from the casting during solidification. The formation of dendrites occurs due to instability in the solid at the liquid interface during growth. In pure metals, for example, dendritic growth occurs when supercooling is possible. Dendrites grows rapidly into the pure metal liquid because of a decreasing temperature gradient into the liquidus. That is the fusion of newly formed solid release heat, which raises the temperature of the liquid to be higher at the solid-liquid interface. The fast-growing part of the crystal advance into the slightly cooler region of the liquid. For example, the secondary arms of dendrites develop perpendicular to the primary arms because as the primary arm solidifies and gives off its latent heat of fusion, the temperature immediately adjacent to the primary arms increase. This creates another temperature intervention in the liquid between the primary arms, so second any arms so that in that direction. A similar argument can be made from the formatting of the dendrites arm. The spacing of the secondary arms is proportional to the rate at which heat is removed from the casting during solidification. With faster cooling rates produce a small dendritic arm spacing. Dendrites starts as long thin crystal that grow into the liquid and thicken. Constitutional supercooling. While dendrites can form to the limited extent in pure metals due to temperature inversion, they are more prevalent in alloys because of the additional undercooling due to constitutional supercooling. Constitutional supercooling arises because of the segregation of alloy element ahead of the solid liquid front. As an alloy solidifies, the chemical composition of the remaining liquid and the newly formed solids continually change. This variation in chemical composition during the solidification process can be quantified from the analysis of the Mesin region on any phase diagram. The extra concentration of this alloying element in the liquid reduces the liquidus temperature of the remaining liquids. If this reduce is sufficient to bring the actual temperature below the liquidus temperature at that point, then the liquid is said to be locally constitutionally supercooled. That is, it is effectively undercooled because of a change in the constitutional of chemical makeup of the liquid. Solidification zone. A metal cast iron into a mold can have up to 2 or 3 distinct zones of types of grain growth. A chill zone, a zone containing columnar grains, and a center acrid-side grain zone. However, it should be noted that all the three zones do not always occur. For example, the solidification structure pure metal exhibit a chill zone and a communar zone both, meaning that contain a center acrid-side zone. The amount of columnar is acrid-side structure in a casting depends on the alloy composition and on the turbulence and the thermal gradients at the liquid-solid interface. A thermal gradient is most easily controlled by controlling the rate of the heat extraction from the casting, or the cooling rate. High cooling rates encourage columnar solidification, while low thermal gradients encourage acrid-side solidification. Alloys that have a wide spread between the liquidus and the solidus temperature solidify with mostly exquisite grain structure at normal cooling rates, whereas alloys with small difference in solidus and liquidus temperature solidify with a mostly columnar structure. This is why cast pure metals typically have a columnar structure. Massive freezing. Alloy with a narrow freezing range solidify with a mostly columnar structure, while alloy with a wide freezing range solidify with a mostly excited grain structure at normal cooling rates. In alloy with a wide freezing range, the formation of the first solidified crystal causes some alloy enrichment in the liquid region of the newly formed crystal. This local enrichment suppresses growth of the first crystal, but creates conditions favorable for the nucleation of the second set of crystals just beyond the first set. The process is repeated as many times as necessary. The grain starts tend to acrid-side if crystal growth is sufficiently suppressed. The dendritic growth also can be suppressed. However, the formation of microsporosity can be a problem in a long-range freezing or massive freezing alloy. This type of porosity occurs that in solidification caused by the inability of the liquid metal to each all of the area solidification. The center region roughly illustrates some microsporosity with massive freezing. Microporosity is particularly different. To eliminate, the most effective method is to increase the thermal gradient, often accomplished by and increasing the solidification rate, which decreases the length of the Mesin zone. This technique may be limited to alloy and mold thermal properties and by casting geometry. In the casting of complex shapes or twin sections of alloy with composites near authentic point are often preferable. non-dendritic solidification of semi-solid processing. Although there are commercial alloys solidified dendritically with either of columnar or an exquisite dendritic structure. An important exception of non-dendritic solidification for semi-solid processing. Semi-solid alloys are produced with a unique non-dendritic microstructure. With important advantage for bulk shaping, semi-solid alloys flow easily and can be ejected into a mold cavity. Much like the injection molding of plastic, this behavior arises from the globular microstructure of the semi-solid mass. During the early stage of solidification, the microstructure of cast alloys can be altered from a dendritic structure towards a roseate or spherical micromorphology. Force conversion, currents of mechanical agitation increase shear and turbulence in the liquid, which promotes the solidification of the globulary semi-solid structure. However, recent research and development so that it is not necessary to use shear force to produce the globulary semi-solid structure. Instead, a slurry with an ideal semi-solid structure can be produced directly from the melt if the temperatures of the melt is such that many nuclei are generated, and if the nuclei do not grow past a certain point or melt back into the pulp liquid. This controlled nucleation and growth concept is the genesis of various processes and the methodologies to generate semi-solid slurries from the liquid states. 5.3 Melting furnace. A wide variety of furnace technology are available for melting metals. In steelmaking, for example, pig iron is produced in a blast furnace from the iron ore, limestone, and coke. Because it contains extremely high level of silicon, magnesite, carbon, and other elements, this liquid iron, together with scrap and fluxing agents, is then introduced into either a basic oxygen furnace or an electric arc furnace for further refining with oxygen. The objective is to reduce the silicon, magnesite, and carbon to acceptability loss level of reducing steel. The steel is then tapped or poured into refractory lines lattice or transferred to the oxigal decarburization vessel for further refining. During the tapping operation, alloying elements that will determine the final chemistry of the steel are often added to the ladle along with deoxiding materials. Steels may also be trapped in the ladle before being poured into molds. The types of ladle treatment used for steel include a variety of common methods, including stirring or heating process for deoxidization, decarburization, and adjustment of chemical composition as the choice of melting furnace depends on the specified alloy, the casting operation, and the required quantities to be furnace. Furnaces vary in size with outputs ranging of the few pounds to several hundred tons. For low temperature melting points alloy, such as zinc or lead, for example, temperature may only need to reach as high 400 degrees Celsius. Fuel sources such as propane or natural gas are usually used to achieve this low temperature. For high melting points alloys such as steel or nickel-based alloys, the furnace may be designed to achieve temperature well in excess of 1650 degrees Celsius. Electricity is typically used to reach this high temperature. For aluminum alloys, the required temperature falls between these extremes. For example, for AlMgSi alloy, typical casting temperature are in the neighborhood of 680 degrees Celsius. And in steelmaking operation and in foundries, the electric arc furnace is commonly used. However, copper furnace are used while large stones are required for iron making. Melting and cupola furnace dates back the several centuries to the old cast type unit that were operated with the hand pump below. Modern cupola furnace may no longer use many manually operation below, but they remain one of the most efficient source for the continuous high volume of iron need to satisfy high production level in manufacturing operation. The cupola furnace is basically a simple cylindrical shaft furnace that produces intense heat that is generated by blowing air through the heat bed of coke. Alternate layers of scrap metal and coke are changed into the top of the cupola, and the scrap metal is heated to the melting temperature by directing contact with the upward flow of the hot gas. The molten metal droplets are collected in the inner portion of the cupola known as the well. Another important type of high-tonnage furnace is reverberatory furnace. Reverberatory furnace have a shallow head for melting metals, which is heated by burners mounted in the roof or in a sidewall of the furnace. The flame used for melting does not impinge on the metal surface itself, but radiate off the walls or the roofs of the furnace, allowing its accomplishment through the additional and solution for metallurgy metal and master alloy. Electric arc furnace. One of the furnaces most commonly used to melt steel alloy in the electric arc furnace. A typical EAF is a refractory line vessel with a bowl-shaped head that is covered with the retractable hemispherical roof. The roof itself may be refractory line, or in the case of large furnace, it may be water-cooled. The roof has several openings through which one or more graphite electrodes can be lowered into the furnace. Alternating current furnaces are favored for producing steel casting and typically have three large cylindrical shaped electrodes that have a thread coupling on the end. These electrodes extrude the electric arc that is used to melt the scrap material change into the vessel. The electrodes float just above the surface of the core ferrous scrap or molten bed that automatically move up or down to properly regulate the arc that is established for melting the changed material. A modern mid-sized steelmaking EAF can produce a quantity of approximately 80 metric tons of liquid steel in time span of roughly 1 hour. The time quote here is a elapsed time between changing the furnace with cold scrap to tapping the furnace. For compression purpose, a modern basic oxygen furnace can produce 150 to 300 tons of liquid steel per batch in roughly 30 to 40 minutes. Electric arc steel making is only economical when there is a readily available supply of electricity that distributes over the reliable electric grid. In many locations, steel mills purposely operate during off-peak hours to take advantage of reduced rates of utilities offer for their surplus for generating capacity. Induction furnace have become a widely used means for melting ferrous alloy and increasingly non-ferrous alloy as well. The key to readily acceptance of induction furnace has been the excellent metallurgy control that can be exercised. Coupled with relatively low pollution and good thermal efficiency, induction furnaces are very efficient, are made in the many different sizes, and are relatively simple in design and operation. Small quantities of materials can be melted rather quickly, which allows metal to be delivered at regular time intervals. A wide range of metals can be melted with this type of furnace, or through little refining of the metal is possible. Induction melting is performed by applying an alternate current through an induction coil, which produces a magnetic field that generates a current flow in the changed material through mutual induction. This generates heat that metal. The changed materials, the amount of energy absorbed by the changing depends on the magnetic field intensity. Vacuum induction melting. Melting under vacuum is an induction heat crucible is a tried and test process in the production of liquidous metals. It has origin in the middle of the 19th century, but the actual technique breakthrough occurred in the second half of the 20th century. Commercial vacuum induction melting was developed in the early 1990, having been stimulated by the need to produce superalloys alloys containing refracts elements within evacuate atmosphere. Crucible furnace. Crucible furnace have historically been the most common type of the furnace used. The record dating back to the dawn of the metals industry some 6,000 years ago indicate their usage. The crucible furnace of an antique were in the form of well-fired clay pots and gave early metal workers the ability to melt metal in the durable container that could be used to pour the molten material into a mold. Few, if any, the molten materials into a mold have a more distinguished history that crucible melting of the metal. Crucibles of earthenware smelting pots that were used to refine copper from King Solomon mines can still be found in this area Asian of Israel. The worst steels of India, the famous Damascus swords blade, and the equally famous steels of Toledo, Spain, were produced using crucible process. Remelting. There are two commonly used remelting processes for metals refinement: electrolysis remelting and vacuum arc remelting. In both processes, an electrode is melted as it advances into the melting regions of the furnace as the working phase of the electrode is heated to the melting point. Drops of liquid metal that fall from the electrode phase are collected in a lower crucible and rapidly solidified. The ESR and VAR methods are very different from each other, and these differences have implications regarding the nature of the defect that can be created by the remelting process itself. The VAR process is carried out of the vacuum, while the ESR process typically occurs under atmospheric conditions, or through ESR under vacuum, or pressure is a variation of the standard ESR process. Other furnace. Several other types of furnace have been deployed for special applications. For example, skull melting is a technique that is used while melting highly refractive metal that would otherwise attack the walls of the crucible lines with standard refractory materials. The traditional method of melting titanium is with a consumed stable titanium electrode lowered into a water-cooled copper crucible while confined in a vacuum chamber. This cool melting technique prevents that highly reactive liquid titanium from dissolving the crucible because it is contain a solid skull frozen against the water cooled. crucible wall. The solidified skulls create a corrosion-resistant protective layer on the containment vessel surface. An electric arc is established between the electrode and the melt pool in the crucible, while gradually melts droplet from the electrode into the crucible. When an adequate melt quantity has been obtained, the residual electrode is quickly retracted and the crucible is stilled for pouring into molds. Vacuum or spool melting was once the dominant method used for melting titanium, but VAR furnaces with static crucible are used in titanium primary melting today. Okay, we next to 5.4 molten metal processing. Molten metal are processed by handle in various ways depending on the alloy and melting particle that are used. Melting is a basic way to combining elements for the purpose of alloying, and the overall chemical composition of the molten alloys must be carefully controlled and processed before casting can take place. The reactivity of molten metals at high temperatures also requires special processing technique for removing and preventing the formation of inclusion, impurity, and dissolved gas in the metal. As noted, ladle treatment may follow furnace melting, as its various examples, or ladle treatment for steel. When a primary furnace emptied into a tapping ladle, the steel can be transferred into other ladles, furnace, or vessel for treatment. Metal loss can occur due to dross formation. Dross is the oxide-rich surface that forms on metals due to their exposure to air. It is a term usually applied to non-ferrous metals, specifically the lighter alloy such as aluminum or magnesium. Dross is normally considered to be an undesirable material, which is supported by the definition found in most dictionaries. Okay, we next to fluxing. Fluxing of molten metals is often the first step of obtaining a clean melt. Fluxing is a term commonly used in foundries and melting department that refers to molten metal treatment from the addition of refractory chemical compounds or inner gas. The various fraction of molten metal is fluxing additivity, either singly or combination. And the combination include removing inclusion, impurity, or dissolved gas from the melt, preventing exercise formation of solid phase inclusion, preventing and or remove oxide build-up on furnace walls, injecting or distributing alloying constituent. Thus, flux are commonly used to some extent with virtually all molten metals operation in both the foundry and in the production of mills products. Fluxing can occur throughout the various stages of melting and handling of molten metals, from the melting or holding furnace to transfer molds. 5. Primary production casting. The primary production of metals normally involves either ingot casting or continuously casting of products such as strips, sheet, wire, or bar. Continuous casting offers certain benefit over static casting, but not at all metals can be continuously cast. Raw products are typically cast in ingot from the subsequent hot working reduction operation. Static ingot casting. Several ingot casting processes have been designed and developed for downstream manufacture process. The most common is static ingot casting, where molten metals is poured into the vertical open mold. The mold is made of metal, usually cast iron, and is tapped along its length so that solidified metals can be easily withdrawn from it. The fundamental requirement that must be satisfied by an ingot are the capacity to withstand subsequent mechanical reduction operation without pelting or cracking, with the capability to yield a commercially acceptable finished product. A number of unreversible events may take place during the solidification of a cast ingot. Shrinkage and gas cavities are some of the most characterized features and common defects in any cast metal. In ingot, these range from a conventional cavity that forms at the open end of the ingot called a pipe and may involve more than 20% of the total ingot length, to internal porosity involving microscopic pinholes. Continuous casting process. Continuous casting may be defined as the continuous solidification with and withdrawal of product from an open shaping mold. The earliest method of continuous casting occurs in the 80s with patents by sellers from manufacturer of lead pipe and by Lake in America from continuous casting of non-ferrous metals tube. Today, continuous casting is a common production method for steel, copper alloy, and aluminum alloy. The quality of continuously cast metal can, in a certain respect, be superior to that of the statically cast ingot. For example, pipe is virtually eliminated. Specify significant production advantage alloy may be realized by reduction of simpling. The subsequent reduction operation traditionally involved in converting statically cast ingots into semi-finished products. The shapes and lengths of an ingot, for example, can have a decided impact of the nature and number of rolling operations traditionally need production plate and sheet production. Casting with expandable molds provides tremendous freedom of the design in terms of size, shapes, and product quality. Expandable molds methods are classified further as either expandable molds with permanent patterns, expandable mold with expandable patterns. Chapter 5.6 Foundry Casting. Foundry use various methods to cast parts with complex shape and interior surface. Molds are made in a variety of ways so that the molten metals poured into the molding cavity result in a part with the shapes and dimension of the finished form. The choice of molding method depends on several factors such as the part size and shapes, quantity toting, and the molten metals being poured into the mold. The most common method is green sand molding, which involves the use of clay to bond sands in an expandable mold. Other types of the sand binder include organic or ergogenic precision. Green sand molds are economical but do not provide the dimensional accords or surface finish of the other bond sand products. Molds are also made of ceramic, plasters, graphite, cements, and other materials. Casting with expandable molds provide tremendous freedom of design in terms of size, shapes, and product quality. Expandable molds methods are classified further as either with permanent patterns and with expandable patterns. Permanent mold casting. Permanent mold casting is particularly sustainable for the high volume produce of casting with a fairly uniform wall thickness and limited in undercuts or intricate internal curing. The process can also be used to produce complex casting, but produce quantities should be high enough to justify the cost of the molds. Compared to the sand casting, permanent mold casting permits to production more uniform casting with closer dimension, tolerance, superior surface finish and improve mechanical properties. In many applications, the higher mechanical properties can justify the cost of a permanent mold when production volumes does not. These metal molds usually made of iron or steel and have a production life of 10,000 to 120,000 casting. Metals can be cast in permanent molds include the aluminum, magnesium, zinc, and copper alloy and hyperreactive gray iron. The vast majority of permanent mold casting are made of aluminum alloy. Die casting. Die casting is generally limited to metals with low melting points. However, high-pressure die casting is one of the fastest methods for the net safe manufacturing of the part from non-ferrous alloy. It is ideal for the economical production of high-volume metal parts with a moderately accurate dimension. For principal alloys, families are commonly die cast: aluminum, zinc, magnesium, and copper-based alloy. Lead, tin, and to lesser extent ferrous alloys can also be die cast. Aluminum is the most commonly used alloy for die casting, followed by zinc, magnesium, copper, tin, and lead. Okay, we next to chapter 5.2 non-ferrous casting alloy. In terms of tonnage, cast iron is the most common foundry alloys, constituting approximately 3/4 of the worldwide production of casting. For example, the 40 census of the world casting production tabulates to the total worldwide production is casting is 2005 at 85 million metric tons. The tonnage of the cast alloys is that year was distributed among the various alloy systems for as follows. The aluminum casting alloy. Aluminum casting alloy are the most versatile of the common foundry alloys and generally have the highest castability ratings. As casting material, aluminum alloy have these favorable characteristics: 1. Good fluidity for filling the dense section. 2. Low liquidus temperature relative to those required for many other metals. 3. Rapid heat transfer from the molten aluminum to the mold, providing shorter casting cycles. 4. Hydrogen is the only gas with flexible solubility in aluminum and its alloy, and hydrogen solubility in aluminum can be readily controlled by processing methods. 5. Many aluminum alloy and relatively free from hot shorts, cracking, and treating tendencies. 6. Chemical stability, and the last one, good as cast surface finish with strong surface that surface few or no blemishes. Copper casting alloy. Copper casting alloys are available as sands, continuous centrifugal, permanent mold, and some die casting. They are generally similar to their work counterparts, but have their own unique composite or property characteristics. For example, the ability to add up to 25% WTPB, which would not be possible for work alloy, provides composition in which diffraction of lead particles help prevent galling in bearing application. Copper casting alloy are used for their corrosion resistance and their high thermal and electrical conductivity. Magnesium casting alloy. Magnesium casting of all types have found use in many commercial applications, especially where their lightness and rigidity are major advantages, such as for chainsaw bodies, computer components, camera bodies, and certain portable tools and equipment. Magnesium alloys and casting are used extensively in aerospace components. Molten magnesium alloys have a very low viscosity, allowing the metals to flow as distance and fill narrow mold cavities. And zinc casting alloy. Die casting in the process most often used for shaping zinc alloy. Sand casting Permanent mold casting and continuous casting of zinc alloy are also practiced, but accounts for less than 10% of zinc casting tonnage. All processes are based on the same family of alloy. We next to chapter 5.8, powder metallurgy. One of these recent metallurgy development in the manufacture of modern alloys is the development of powder metallurgy processing. Metal powder can be produced using a wide variety of mechanical methods as well as by chemical and electrochemical methods. Atomization is the dominant method for producing metals and prealloyed powders from aluminum, brass, iron, low alloy steels, stainless steels, tool steels, superalloy, titanium alloys, and many others imported industrial alloys. Water atomization. In terms of tonnage, water atomization is now the premium mode of the atomization for metals, especially ferrous metals powders. The large commercial application of water atomization is iron powder from press and sinter application, and approximately 60 to 70% of the world's production of iron powder, which now totals more than 600,000 metric tons per year, is produced by water atomization. As a general criterion, any metal or alloy that does not react violently with water can be water atomization, provided it can be melt and port certification. However, it is found in practice that metal stand that melt below approximately 5 degrees Celsius give extremely irregular powders due to ultra rapid freezing, which can be understandable in certain alloys. Thus, since in the lowest melting temperature metals produced commercially in this way. Gas atomization. Gas atomization process generally produce powder particles that differ from those produced by water atomization process in terms of their geometric and surface chemistry. Gas atomization powder are typically most spherical in geometry and possess a lower surface oxygen content than their water atomization counterparts. During the gas atomization process, the liquid metal is dissolved by a high-velocity gas such as air, nitrogen, argon, or helium that is dragged through a specifically shaped nozzle. Atomization occurs by kinetic energy transfer from the atomizing medium to the metals. In order to visualize this process, the breakup of the metal stream into the fine droplets can be compared to the way that gasoline is atomized as it passes through the Venturi nozzle in an automobile's carburetor. Gas atomization differs from water atomization in several respects. Rather than being dominated by the pressure of the medium in water atomization, it is found that the gas-to-metal ratio is the dominant factor in controlling powder particle size, with the median particle size being related inversely to the square root of the gas-to-metal ratio. Okay, that's all from me. If you have a question, you can write below in the comment section. Thank you for all.